Good morning, everybody. Thank you for coming to this first session so early in the morning. This is quite a large room, so there's a lot of ability to watch. If you really want to come forward, there's a number of seats in the front you can get and see it. So we've got, this is a session on cities on subduction thrusts. And just to remind the speakers here, we're going to have, there's 15-minute talks, so we have to get them with 15 minutes. There will be a green light for the first 12 minutes, and then there will be a summing up. If the yellow light will come on, and you should sum up during that time. And by the time the red light gets on, you should be done. And we can't have any more questions after the red light is there, and we have to switch different people. Okay, so then our first speaker is an invited speaker. John Vidali is going to talk about the Seattle, seeking the balance between the Space Needle, Starbucks, the Seahawks, and subduction. Thanks, John.
Oh, all right, well, thank you. Okay, didn't really expect a 1,000-person auditorium. I'm really just giving an update on the kind of threats of the subduction zone in the Seattle region. There's nothing really kind of earth-shaking in this talk. Let's see, how's this mouse actually go on the screen? Press the buttons. Okay, well, I don't want to change the slide yet. We'll assume it'll work. So my hope is that you'll see that we have more than dowsing rods. Those are dowsing rods in the upper left. And I also want to thank Art Frankel, Kate Alstead, and Paul Bowden for contributing some of the material I'll talk about today. Yeah, that works. So the tectonic setting is probably well known to most of you. Oh, well, shoot. Do we have a pointer?
Right here.
Okay. So the tectonics are that we have a subduction zone. The subduction zone threatening Seattle is the one that runs from Canada down to California, 1,000 kilometers or so. And because of this subduction zone, in which the Juan de Fuca plate and a couple little plates on either side are pushing under North America, we have not only a megathrust zone that has big earthquakes, very big earthquakes, but we also have earthquakes within the subducting slab as it crumples, and we have earthquakes in the crust above. And just to zoom in a little bit, we know that these earthquakes that break the coast are about magnitude 9. I'll talk a little more about those in a minute or two. With the earthquakes underneath in the deep slab are about 50 kilometers down, about magnitude 7. And the crustal earthquakes are about magnitude 7. So we have three kinds of earthquakes that threaten Seattle and the Puget Sound. In detail for the subduction zone, we have seen a lot of analogies to these events. Very similar events happened in Sumatra. It killed 200,000 people 10 years ago. In Male, Chile, that killed a few hundred people. And in Japan, a couple of years ago, that killed about 20,000 people. And one of the just lessons in general is that we get surprised whenever we have one of these earthquakes at what the damage is. So it's something we need to study carefully. We have this special case that people didn't recognize the Cascadia subduction zone had great earthquakes until the 90s. So a lot of the infrastructure was built without having those kinds of strong motions in mind. And there's a lot of things we don't know about this subduction zone. One is just how close does the earthquake break to the Puget Sound? We don't know what that lower limit of rupture is. And therefore, we're not so sure how strong the shaking will be in these big earthquakes. And something we'd really like to know that we don't have a clue is when the earthquakes are coming. Of course, earthquake prediction, according to most of us anyway, aren't working at all. And we even have difficulty telling when we're late in the seismic cycle to expect earthquakes to be more likely. So here's a scenario that Art Frankel constructed, and this black line just indicates the possible limits of rupture of this earthquake. And again, you can see California up to Canada. And you can see the edge of rupture maybe comes halfway in from the coast toward the Puget Sound. We really don't know. The last earthquake was in the year 1700, and we know the day and even the likely hour from the tsunami in Japan, which agrees well with the geology on the coast. And from the offshore studies, and Chris Goldfinger is critical in this, we know these earthquakes come about every 500 years. So every 500 years we have a magnitude 9. The last one was 300 years ago. That's a roughly 10% chance every 50 years. But this late in the cycle, 300 years into the 500-year cycle, the best estimate is it's about a 14% chance every 50 years of having this earthquake. Okay? So not a huge chance, but one that we have to prepare for. This is a scenario constructed by Andy Delory in conjunction with Art Frankel. And here he just did a magnitude 8 in the northern part of the subduction zone. And what you see is the peak amplitude colored in. Of course, it shakes strongly up here near the coast, 100 centimeters a second peak velocity. And at the distance of Seattle, the amplitude's much lower, about a factor of 10. But the basins around Seattle, there's the world-class sedimentary basin, the Seattle Basin, there's also Tacoma Basin, the Everett Basin, amplify the motion by a factor of several. So you can see if there's even a magnitude 8 on the coast, we get large amplitudes and long duration, about a minute long in this magnitude 8 simulation. So we get real problems from the basin for these subduction earthquakes. One thing this does give us the possibility for is earthquake early warning. Because we have such large distance scales, when one of these earthquakes gets started, we think that we can show there's a fair chance that it might run all the way. And the running all the way takes 5 or 7 minutes for the shaking to get to the city if it starts kind of the furthest point in the subduction zone. And early warning can have some useful responses in this case. And the typical things we think about are slowing down the traffic, getting people off the bridges and vulnerable things like the viaduct downtown. The airports can cease operations temporarily. Hospitals and emergency managers can begin to prepare before they're feeling the strong shaking. And companies might fortify their computer systems or back off their fragile manufacturing equipment when they know that shaking's coming in a few minutes or there's a 50% chance of shaking. And one advantage here is we don't need to make any scientific discoveries. The physics of wave propagation has been known for many decades. So we're in the situation where we're making a prototype that we think will be working within a year for an experimental way. And we're still trying to document that early warning is worth, the fairly significant cost it would cost. And I'll have a talk about this Friday morning if people want more details of how we're doing this. So the megathrust isn't the only threat. In fact, it's at least as much of a danger to have these faults in the crust. There's faults under Seattle. There's another fault called the Tacoma Fault, one called the Olympia Fault. There's also the South Whidbey Island Fault running up the east side of the Puget Sound. So these littler faults are closer in and can in fact cause more damage than a megathrust if they hit in the wrong place. And the number on this is about 15% per 50 years, that we should have an earthquake on one of these faults bigger than magnitude 6.5. And this is sort of a guess. It's roughly consistent with the geodesy, the deformation that we can see. But it also comes from extrapolating the small earthquakes up to the bigger earthquakes, which isn't a certain process. So here's the location of the deep earthquakes. We've gone from these shallow faults, the Whidbey Island Fault, the Seattle Fault, to the ones within the subducting slab. You can see they're also concentrating under the Puget Sound, and we have 3 or 4 main ones. There's 2001 Nisqually is the one you probably remember. Upper magnitude 6s caused several $1 billion worth of damage. 1965 and 1949 had similar events. There's lesser events spread across the region, getting deeper as you go to the east because of the dip of the subduction zone. And these are hard to get a handle on as well. We have 3 or 4 instances of big ones. There maybe weren't so many in the half century before that. They've hit in the Puget Sound, but there's subducting slab all the way from Canada to California. Any of those could have it. We've seen upper 6s, but globally, we've seen earthquakes as big as 7.5 or even bigger in such settings. So there's a lot of unknowns and just pure guesswork in estimating the risk of these. Here's an example of the difference between a deep and a shallow event. Here's the shake map for Nisqually, and here's the shake map for a hypothetical, I think it's a 6.7 under Seattle. And you can see more intense shaking for the crustal earthquake, but a much wider area that's moderately shaken for the deep earthquake. So two quite different scenarios. And to kind of drive home that this really is a problem for East Seattle, Art Frankel has made a hazard map. I think it's the best hazard map in the world. He took all the plausible faults to shake Seattle on the coast and within the crust and deep, and ran finite difference simulations through three-dimensional models of the basin structure and put in the right near-surface effects and color-coded it. You can't see it, but these are quite strong motions. Brown is the worst, red is bad, yellow is not so bad. And circled in blue are the areas of the unreinforced masonry structures. And you can see they correspond pretty well with the areas of which shaking is going to be the worst. So Seattle, the city of Seattle is working pretty hard to figure out a plan to try to fix all these old buildings facing the traditional obstacle that it costs a fortune to fix the unreinforced masonry problem. So one thing we're trying to do is just understand the problem better. The survey has made a new kind of instrument, netquakes. Jim Lutgert's giving a talk about this later this week. Basically $3,000 instead of $10,000 for a seismometer. So we've put 100 of these in the last year or two in Seattle. We put about 15 more in Portland. And in fact, just last week there was a magnitude 3.2 earthquake under Portland, which has greatly increased what we know about the distribution of shaking across Portland. So we're learning things. Another thing we face in Seattle is liquefaction. We're sort of the liquefaction capital of the country. Seattle has liquefied 3 times that we know of in the last century because of these deep earthquakes. And it's a particular problem in downtown. It's soft soil. In fact, some of the downtown was made by just hosing off the hillsides and piling up the dirt under where they built Pioneer Square and places like that. And this is the viaduct cross-section, and the seawall is held back by wooden pilings that are rotting and being eaten by insects and in soil that will liquefy. And equally bad is the construction of the viaduct. So it's 50-50 chance which one gives first. So liquefaction causes us a lot of problems. And, whoops, does this work? And, sorry. And so in response, we've also instrumented a liquefaction array in the heart of the industrial district of Seattle. And if we're lucky enough to have another liquefaction event, we'll have probably the best data set in the world to try to understand liquefaction with both pore pressure sensors and seismometers at depth, which is a very hard phenomenon to capture. Okay, and then landsliding is another problem. This is the work of Kate Alstead. And here she's done a simulation of a magnitude 7 earthquake on the Seattle Fault. She's run it through the 3D basin structure with Art Frankel. And she's put in the topography and the superficial geology with the Newmark method. And just said what would happen. And what happens is, not too bad if the soil's dry. About 5,000 landslides, 150 buildings affected. She's charting what critical lifelines it would affect. But if it comes in wet conditions, saturated soil conditions, you get 30,000 landslides, 1,500 buildings affected, and you can see the color coding, percentage chance that there'll be slides in these areas. There'd be slides all over the city. So landsliding is another of our problems. And I haven't touched on some of the other subduction-related problems. Here's the kind of shadow of Mount Rainier. Rainier has lahars that run into South Seattle. Of course, big earthquakes on the coast can make waves. Even earthquakes on the faults in Seattle can make seiches in the Puget Sound and Lake Washington. Maybe I'll finish early. So just to wrap up, we know something about the hazard, but there's a lot we don't know, and good reason for us to keep working. In dollar terms, the Puget Sound is roughly at risk of losing $500 million a year. Of course, most years we lose almost nothing. A few years we'll lose a tremendous amount. So it's hard to keep focus on a problem that's as long-term and as serious as this. And so what we're doing at the moment is just looking very carefully with ever more instruments, doing 3D modeling of the hazards, and we're trying to do what we can with early warning to give people at least a bit of a heads up when one of these big earthquakes is underway. Okay? Thank you.
Thanks, John. We have time for a couple questions here. Can't see. Ready?
No, I think.
Do you see anybody? Yeah.
So I'm curious, which of the sources, is it the Crustal faults, the sort of deep slab earthquakes, or the big megathrust earthquakes turn out to be the biggest drivers of the loss of the stress, considering the different probabilities of each type?
Yeah, that's a great question. And for a particular site, the local earthquakes are the worst problem. For example, the viaduct, the highway through downtown, has gates now that the highway department put in. If it shakes enough of the majority of the instruments, these gates drop and try to clear the road. And people calculated which faults were the dangerous ones, and 90% of the earthquakes that would knock down the viaduct would be a Seattle earthquake. So, of course, the coastal earthquake has a much wider zone of damage. For any given spot, the local earthquakes are the issue. And, you know, if you drop gates and there's a local earthquake, you're really not going to clear that many cars before the worst shaking hits. So it's a tough problem. Okay.
Okay. Thank you very much, John. We'll move on now. The next speaker is Andrew Delaray, and he's going to talk about the effects of source and path heterogeneity on simulated strong ground motions from great earthquakes on the Cascadia subduction zone. Thanks, Andrew. There's the pointer here. Okay.
Okay, thank you all for coming. That last talk was a good introduction to what I'm going to talk about. I'm going to be focusing on large subduction zone events, and this is work I did with the USGS in the past year with my co-author Art Frankel. I'd like to acknowledge FM Global and USGS for funding this study, as well as the contributions of Pen-Cheng Liu and William Stevenson. So I'm going to be talking about the Cascadia subduction zone, although the points I'm making really apply to any large event. So I just want to get you situated here. So the Cascadia subduction zone is off the coasts of Northern California, Oregon, Washington, and British Columbia. The most recent magnitude 9 event was in 1700. The recurrence rate for magnitude 8 or greater is somewhere around hundreds of years. And in the instrumental record, seismicity is almost non-existent on the subduction interface. Now, the subduction interface can be divided into a locked zone and a transition zone. The locked zone, as the name suggests, is thought to be almost completely locked, and the transition zone is thought to be partially locked. And one of the questions, as John alluded to, is that we don't really know to what extent the transition zone will participate in producing strong motions during a megathrust event. So since we don't have an instrumental record, we have to use other kinds of tools to make strong motion predictions. And the most common is these attenuation relationships, which relate magnitude, distance, and frequency to strong motions. And what I'm going to introduce today is a way to account for both source and path complexity and make these models a little bit better. I just have a couple of examples up here. On the left-hand side is an attenuation relationship, which is the red curve, and some data points from the Tohoku earthquake. And on the right-hand side is a magnitude 6.6, also in Japan, on Japan's west coast. And I just wanted to show you a couple of things that attenuation relationships have trouble modeling. On the left-hand side, for distances greater than about 100 kilometers, the attenuation relationship here overestimates the ground motions. That may be due to a lot of the moment on that event was the slip near the coast, near the trench, which didn't contribute much to strong motions on shore. On the right-hand side, I highlighted some points that are in a sedimentary basin that are not accounted for by just looking at the magnitude, distance, and frequency. So my first main point is that the empirical attenuation relationships do not consider source complexity, which includes the distribution of asperities or sub-events and location of the hypocenter. So what I'm going to do is I'm going to try to model that source heterogeneity. On the left-hand side, I have a rupture model that covers probably about 80% of the subduction zone, so this would be a magnitude 9 event. Now, the distribution of asperities is arbitrary, but it's instructive on what kind of effect the source heterogeneity will have on strong motions. So on the right-hand side, I'm going to show a simulation. You can see that the hypocenter is up in the north, up here. And what we're going to see is we're going to see source heterogeneity by seeing stronger motions near the asperities, which are in red, and we're also going to see some basin effects similar to what John showed earlier. So rupture propagates to the south, and you'll see the basins up here get strong shaking. That's a path effect. We also see stronger shaking near the sub-event. So I'll do that just one more time, if I can find my mouse here. Here we are. Just to see that again. And so we're really seeing both source and path heterogeneity here that would not be captured by an attenuation relationship. Okay, so I actually ran this 3 times with 3 different hypocenters so we can see how the hypocenter location will affect strong motions. This is the south hypocenter down here. In the middle, I have the peak ground accelerations. The color saturation is at 25% G. And on the right-hand side, I have the peak ground accelerations plotted against the attenuation relationship of Zhao et al. And I've broken it up geographically so we can get a sense for how each region is affected differently. So if we start in the north, we can see that there's pretty good agreement between the 2 models, except for the fact of the sedimentary basins. The shaking is considerably stronger than what's predicted by the attenuation relationship. In the central area, there's good agreement, and in the south, the predictions from the finite difference simulations are actually less because of a south hypocenter. Most of the energy is directed north. So these are features that would not be captured without this kind of a 3D simulation. If we move up to the central hypocenter, this is kind of a best case scenario for the region because this is a bimodal rupture, and a lot of the energy goes north and south, hits some points along the coast, but some of the inland areas where people live have less shaking. And as you can see over here, if we look geographically, the attenuation relationship over-predicts the strong motions relative to my finite difference simulations. Now, this is the north hypocenter, and this is actually the worst case scenario because with rupture going down to the southeast, a lot of the energy is directed at western Washington. And we also, because of this sub-event down here, the southern coast of Oregon gets hit pretty hard. We can see the basin effect here. We can see the midsection, because there's not a big asperity off the coast, does pretty well. And then up here we see some strong motions along the southern coast of Oregon, which we see up here. That's due to the directivity coming off of this sub-event. So my second main point is that the empirical attenuation relationships do not consider path complexity. Mostly I was looking at source complexity on the last set of slides, but we can have path complexity, especially produced by mid or upper crustal structures like sedimentary basins. So what I have here is similar to what John showed you earlier, where I have, this is for the magnitude 9 event with the north hypocenter. Notice that the basins really light up in this scenario. So I have 4 different traces, 1 on the coast, 1 inland that's not in a basin, and 2 that are in the basin. And so if we look at number 1 and number 2, that's on the coast and inland, we see that the inland station has much lower levels of shaking just due to its distance. But if we move into the basin, we see both higher amplitudes, and we also see these big surface waves that are produced by the basins that trap and convert the energy. And you can see that up here as well. And then my third point is that, okay, so now if we can model both the source and the path complexity, then we can investigate how different rupture models affect ground motions. And one of the things that I mentioned at the beginning, and also John mentioned, is that one of the questions is how far down dip we have seismic radiation that will produce strong motions, and especially in the populated areas. And so the attenuation relationships would only consider distance, but there are other factors, and this is a good tool to investigate these kinds of questions. So I'm going to investigate how the down dip limit of the rupture affects ground motions. And so what I did was I got a magnitude 8 event off the coast, and I ran it twice, once in the locked zone and once in the transition zone. Now, this isn't necessarily a realistic scenario in the sense that we won't necessarily get slip in one or the other. It could be both. We don't really know, but at least this is instructive on how each of these regions would contribute to strong motions in the populated areas. So in the middle, on the top, this is the locked zone event, and this is the transition zone event, and this is peak ground accelerations with a saturation value of 25% G. And if we look at the up dip or the locked zone rupture, we can see that it looks pretty well behaved in the sense that the attenuation relationship does a good job of making predictions, or at least being consistent with the finite difference simulations, with the exception of some of the basin effects. And so this rupture is more in the far field, so it's going to behave a little bit more like not quite a point source because it's not that far away, but it's going to be sort of well behaved in the sense that the source heterogeneity isn't going to play as big of a role. If we move into the transition zone rupture, you can see that there's a lot of scatter here. So when the rupture is in the near field, then the source heterogeneity plays a huge role in the distribution of strong motions. What you can see here is that for the down dip areas, for the northern section, so this is up here, it does pretty well. Most of the strong motions actually go north because of the location of the hypocenter. If we go down to the south, actually, because of the location of the hypocenter and the largest disparity, most of the energy goes north, and so the southern coast of Washington actually gets less shaking than it did with the rupture further away. So even though in general shaking is increased when you move the rupture closer, the source heterogeneity plays a much bigger role. So I just wanted to review my main points. So the empirical attenuation relationships do not consider source complexity, which includes the location of asperities and subevents and the location of the hypocenter. They also don't account for the complexity, path complexity produced by mid or upper crustal structures like sedimentary basins. And the down dip location of the rupture generally increases strong motions the further down dip, but those distribution of shaking is highly dependent on the location of asperities in the hypocenter. That's it.
Thank you very much. Thank you very much. Andrew, we have time for some questions. Yes, back there.
No, the velocity model itself does go down that far for the particular scenario that I ran because the rupture was further north. I didn't include that in this simulation, but that is part of the larger model.
Oh, yep, over there.
Yeah, in that particular scenario I showed you, the reason why the shaking was a little bit less in Seattle is because of the relationship between the hypocenter and the largest asperity, so a lot of the energy was directed elsewhere. In general, Seattle is more at risk for like a crustal event. I mean, shaking would be stronger for a crustal event than it would be for a subduction zone event, I think, in most cases. You know, if the crustal event were somewhere in this sort of 6.5 to 7.5 range.
Yes, over.
When I was looking at the attenuation relationship, it was the shortest point to the rupture surface.
Okay. I have one more question. The tsunamis seem to be the biggest effect on some of the populations in the recent earthquakes. Have you been working at all with tsunami modelers to try to see whether your different scenarios make any difference to tsunamis?
Not directly. There are people working on that problem, and some of these, the geodetic signal for some of these simulations could be used for that kind of a study.
Thank you. And Michael Bostock will introduce our next speaker.
Well, we're going to shift gears now a little bit and move away from Cascadia. Our next talk is an invited talk, and it is entitled Depth Limits and Time Variations of Slip in Subduction Zones, Lessons from Alaska and Elsewhere. And speaker is Jeff Freimuller. F5, okay. And now we need to go into the next talk.
Okay, thanks. So one of the differences, of course, in Alaska is we've had the big subduction zone earthquake, so we can look at some different sort of problems than we do in Cascadia. I deleted the last few words from the title because I actually ran out of time to talk about elsewhere. There was too much going on in Alaska. So this is downtown Anchorage on a nice winter evening. And this was downtown Anchorage in 1964 after the earthquake. So what you see here are ground failures that were actually caused by shaking-induced surface failure. So all of those, in fact, the bluff sort of collapsed. So this is another example. And another one here, this white surface here was level with that prior to the earthquake. So what all of those failures were ultimately bluff failures. So there's a coastal bluff. And here, this is the downtown area. This is what's now called Earthquake Park over here. This was a residential neighborhood. And essentially, the bluff was here before the earthquake. All of that material failed out into the ocean as a result of the shaking. So that was the biggest impact, direct impact to Anchorage was from these ground failures. All right, so Anchorage is located about there, right near the edge of this orange spot. This is a co-seismic slip model for the 1964 earthquake. This one's from Suito and Freimuller, although if you look at others, for example, Ichinose et al., 2007, they look quite similar. The red colors are the areas of very high slip. So in our model, this is greater than 20 meters of slip. And this blue area is, in our model, less than 5 meters of slip. So much, much lower than the 20 meters, although 5 meters is still plenty of slip, but not at all like 20. So one of the things that's interesting here is there's a gap between the area of very high slip and Anchorage itself. It's perhaps as much as 100 kilometers away from the area of very high slip, although it may have been a bit closer than that. Of course, the geodetic data in 1964 was triangulation. It's somewhat limited in its precision, but it does actually rule out that we had 20 meters of slip coming this far inland. Now, this orange area is an area of a slow slip event from Ota et al. 2006. So this was a 1998 to 2001 long-term slow slip event. And so what I'll be talking about is where is the limit of slip, essentially how close does the slip get to the city, and what are the processes that might control that. This is a picture of what we call slip deficit based on the recent geodetic data. So it's based on 10 to 15 years of GPS velocities, and we're essentially determining which parts of the subduction zone interface are slipping and which parts are stuck. So the red parts are the stuck parts, or locked parts, and so we call it slip deficit because this is the area where slip is not occurring on a regular basis, so this presumably builds up to slip in the earthquakes. The slip deficit region actually goes a little bit farther inland than we think the co-seismic slip did. But otherwise, it generally matches the pattern. So high slip here, low slip in this section, and high slip was the earthquake pattern, and that's essentially matched. to first order by the slip deficit. So here we have a wide region, a little bit along strike, a much narrower region, and again, that matches what is observed in the 1964 earthquake. So some of the key questions for hazards are what is the down dip distribution of slip in major earthquakes, and how well could we predict it based on pre-earthquake observations? So if we only had the GPS and made a model based on the GPS, how well would that match what we actually know about the earthquake, and how if we do this in another location, can we draw a parallel essentially to this? Then how variable in space is the down dip limit of the slip deficit and thus down dip limit of the slip? And how variable in time is the down dip limit of the slip deficit? Because we have transient events. We know of this slow slip events in many subduction zones. In Cascadia, the very famous ETS events. And we actually have evidence in Alaska for some other transient events as well. So I'll look at these transient events. Here is the same slip deficit picture again. And I want to call your attention to, first of all, this little blue spot here. This is based on GPS velocities that actually averaged over the time of the slow slip event and the time before and after the slow slip event. And so as a result, in the slip model, this blue area was slipping faster than the normal plate motion. And that's because part of the time considered in the velocity solution included the slow slip event. But we also see other transient events down here in the area around Homer in Lower Cook Inlet. And those are actually located very close to this edge here, a lateral edge of the main asperity. So I'll look at both of these in the remainder of the talk. Actually, first we'll start out up here, looking at the slow slip events in Upper Cook Inlet, and then these transient events in Lower Cook Inlet. So here's a GPS time series from one site in the vicinity of that large slow slip event that I showed you before. What we show here is the north component time series and the vertical component time series for this one particular site. So when the site was installed, it was moving southward towards the trench, and this was during the large slow slip event. It then turned around and started moving northward. This is the 2002 Denali earthquake, which was a few hundred kilometers away, but nevertheless produced a small offset. And then the site continued moving northward, but essentially the time series sort of rolled off, and in the recent year or so, it's been moving not at all, essentially, in the northward direction. It's interesting to see that the vertical actually kind of matches a similar pattern. It was uplifting when it was moving to the south, not so much, a little bit of uplift, but not so fast when it was moving northward, and then uplifting again when it started rolling off. So this blows up the more recent time period, and if we have a period of steady deformation, we might predict that it should continue along that linear trend. So we can estimate the deformation or the displacement due to the slow slip event by essentially taking the difference between the observed trend, which is the blue, and this predicted linear trend. So this is from a poster. I forgot to mention it here. Actually now former student Yuning Fu's poster, T13F 2698, this afternoon, so he'll have the details of this. And what he's done is broken up this ongoing event into a phase one where there was sort of a variation, like an acceleration of the slow slip event displacement, and then a phase two where things were a bit more linear in time. And if you look at slip models for the two phases, this is phase one, this is phase two. Phase one involved a larger area, and it involves a larger total displacement and total slip, but that's also because it's a longer duration. There's more time in phase one than there was in phase two. Phase two actually showed a concentration of slip in a smaller area. But if you compare the slip rate, which is the number to the right of the bar, the peak slip rates here were actually pretty similar to the peak slip rates here. So what's changing is not so much how fast the interface is slipping, but actually the area that's slipping. And actually, both of these events are smaller than the 1998 to 2001 event, which extended further up dip. So now let's move further down to the Lower Cook Inlet region. This is the white velocities come from a compilation I did a few years ago. In this area, almost all sites have data only prior to 2004. The black velocities are from 2004 to 2010. And if you look over here and compare closely adjacent sites or the same sites, the velocities are very similar. But clearly you can see that here they're quite different. So the white velocities are towards the trench, much faster in that trenchward direction than the black ones. And so we saw a coherent and systematic change in the deformation pattern. And it turns out to be fairly abrupt, occurring in 2004. What I'll show you now are time series of sites along a profile here from the Pacific coast across Cook Inlet. So AC35 is the closest one to the coast, and then we'll go across Cook Inlet. So here is the Pacific coast sites. Here is the across Cook Inlet sites. And I've detrended the time series based on the 2004 to 2010 time interval. So we only have one continuous site that goes before 2004, and it actually shows a fairly abrupt change. This change has to happen within a few months, but we have campaign sites that also show the same kink at the same time. The other continuous sites were built after this first change, but they show you the second change in 2004. And essentially all the sites show you the same coherent change. So we have a velocity change in 2004, a velocity change in 2010, and actually this velocity change in 2010 takes velocities back to something pretty close to what they were before 2004. And if we compare what kind of model might explain that, essentially the difference is that in 2004 to 2010, we would need about a 40-kilometer additional width of the locked region. That is, a section of the subduction zone that from at least 1995 to 2004 had been creeping, basically locked for a few years and stopped creeping, and then apparently started creeping again after 2010. Now, this is the same figure, but I've extended it to about 2 weeks ago. And what's interesting when you do that is actually in late 2011, early 2012, we see things sort of kicking back upward. So actually yet another change in the pattern. And again, it's relatively abrupt and regionally coherent. So velocities change again around late 2011, early 2012. And if we look at this Pacific coast site, AC35, these two red lines are actually drawn by eye, but they are parallel. Okay, so this one is approximately the pre-2010 trend. This one is parallel to that, and it shows you the 2011-2012 trend, which is again quite similar. Here is that intervening period from early 2010 to late 2011, which was different. So really it's quite dynamic. What we see is, first of all, there is a first-order correlation of the slip area in 1964 with the slip deficit area over the last 15 years. But there's an interesting and potentially important difference in that the slip deficit area extends further down dip than the area of large slip in 1964. However, some of that area of slip deficit seems to be essentially eaten up by slow slip events and transient events that we've observed. There have been multiple slow slip events down dip of this major 1964 asperity. They occurred in an area that had little or no slip in 1964. But there's still a gap between the areas of the slow slip events and areas of greater than 10 meters slip in 1964. So the question is, should this be filled by further slow events that simply extend further up dip? That might be a reasonable conclusion, given that we've seen a variation in the spatial pattern of these slow events. Or potentially, are they filled by smaller earthquakes, like magnitude 8 events that would occur some point in the future? And then further along strike, the down dip end of the slip deficit area in lower Cook Inlet has shifted multiple times, although so far at least all within a range of about 40 kilometers or so in the down dip direction. So that corresponds to actually a relatively narrow depth range because the dip angle is only a few degrees here. So we're really just seeing a change of a few kilometers in the depth of this down dip limit. But because the dip angle is so shallow, it maps into a very large lateral change. So to get back to these key questions for hazards, the first one, what is the down dip distribution of slip in major earthquakes and how can we predict it? Well, based on Alaska, I think we could say we should be able to predict it to first order from the pattern of slip deficit. we should be able to tell the difference between very wide and very narrow regions of slip in the great earthquakes based on very wide and very narrow regions of slip deficit. However, we do see that this varies. Certainly in Alaska, the width varies by more than 100 kilometers of the slip area. Again, that's modest, more modest in terms of depth, but still very wide in terms of impact. And perhaps more importantly is that this limit is varying by tens of kilometers over time scales of a few years in time, at least in certain regions, although apparently not in other regions. So we don't understand why some areas are showing these and others are not. Perhaps it has to do with edges of these disparities. Thank you.
Thank you. Do we have any questions for the speaker? John.
Yeah, so the two questions, if you couldn't hear them, were first about tremor. Is there any tremor associated with these events? And what about other things not on the megathrust? First of all, for tremor, the big slow slip event here definitely had tremor. So this event definitely had tremor associated with it. This one, it's not so clear if there has been tremor associated with these changes. There hasn't been as systematic a look at tremor as there has been in Cascadia, but there definitely was tremor here and has been tremor associated with other, perhaps smaller slip events there. As far as shallower events, there are deep crustal events in Cook Inlet. And so those get up to the magnitude 6.5 to 7 range. We probably don't have local crustal faults like the Seattle fault equivalent in Anchorage, at least based on what we know of the geology. But these Cook Inlet events, if they occurred closer in, could pose a significant hazard.
Thanks very much. I think in the interest of time, we had best proceed. The next talk is given by Alfred Hearn. It's entitled, and a list of co-authors, it's entitled New Features Revealed by Multi-Method Seismic Imaging of the Seismic Structure and Activity of the Lesser Antilles and Hellenic Subduction Zones and Their Comparison with Tohoku.
Thank you. Could you show me? Okay. Sorry.
Yes, so
Up and downs.
the up and downs, I think you just need, just the arrows.
Okay.
And this is your pointer here.
How does it work?
Just press that button, that's right.
Thank you. I'm going to bring you to more exotic places where seismic hazard due to subduction hasn't been a main concern. But there are two active subduction zones in the European Union. One is the Western Hellenic Arc here. The other one is the Lesser Antilles Island Arc subduction. There are two French islands there, and both of them had their capital city destroyed in the mid 19th century, and now have a population of over 1 million people. And in Greece here, you have had at the turn of the 19th to 20th century a series of magnitude 7 to 8 earthquakes, and this 365 earthquake which destroyed by a tsunami Alexandria of Egypt and caused large damage. So this has been the reason of our interest for these regions. In both cases, you see here, for instance, the GPS vectors of the Aegean region, which show that the upper plate is displacing towards the subduction zone, which is the same here also in the Antilles region. In fact, in the study of Schross and Campos of 95, modeling the coupling coefficient of subduction zones without, of course, looking at these ones, which were minor ones, full seismic coupling is in fact expected when the upper plate is directed trenchward. This had outliers by that time, which are namely Sumatra and Tohoku, which since then have been seen to conform to this rule and be fully coupled. And probably because of the Sumatra 2004 earthquake, we were successful in having funding. We were looking for a decade to go and work on these subduction zones. So we could afford here an experiment which brought together, this is 100 kilometers, Guadeloupe, Martinique, the French territories, and other islands of the arc here. We could record here a series of multi-channel seismic reflection profiles all along here over a grid of 100 OBS. You have to get your feet wet and your seismometers wet in this region because the forearc is submerged. And we also recorded the earthquakes for 6 months on this array, as well as 2 long refraction transects over OBS from the accretionary prism to the back arc. In fact, the size here is on the order of the same size as for the Tohoku region from the volcanic arc to the deformation front. This is the same scale, but here the islands are so small that you have to do everything underwater. In fact, part of this is of the Lesser Antilles subduction zone from the deformation front here, at least 120 kilometers, is a wide accretionary wedge, which is different from the Honshu case where you have only a few tens kilometers of accretionary wedge, and of the Sumatra region here where you have high velocity material lying on the plate boundary here, which is rather a forearc, and where the rupture of the 2004 earthquakes ruptured the whole interface from here, the deformation front, through the crustal thrust, crust on crust, and even down partly into the under the mantle wedge. So we are looking, in fact, to try to see with seismics whether we can see in the 2 regions of interest a measure of the seismogenic zone, for which a proxy, a usual proxy, is to look at the crust on crust interface, thinking that the mantle part can be decoupled because of serpentinization of the mantle material by fluids from the slab. Here is just some examples of the northern part of these are multi-channel seismic reflection lines from the deformation front to the inner forearc. You can follow here the subduction thrust, and you see that even under the accretionary wedge, you have a heterogeneity of the subduction interface. You have here this ridge, which is a Barracuda ridge, in fact, a ridge inherited from the history of the Atlantic Ocean, which deforms differently the accretionary wedge, and even here in this northern part, deforms the forearc basement. So there must be different coupling, different seismogenic coupling in different parts of this arc, and we can map this out. The other point is we can map out here the edge of the trenchward tip of the forearc backstop, which is a proxy of the up-dip limit. And we can follow this over the profiles here. You see the deformation front is out here, the volcanic axis is here, and this is the up-dip limit of the upper plate basement, which can be taken as this up-dip limit. So what about the down-dip limit? The down-dip limit is usually taken in this simple approximation to the seismogenic zone as, say, the mantle thrust, which in the case here of this is an example of a profile in the Alaska-Aleutian Island arc, subduction zone, where you have here, the scale is here 10, 20 kilometers. You have a thin crust, which is thickened here under the volcanic arc, and this interplate here is of limited dimension, whereas the refraction seismic line over this OBS through the Lesser Antilles arc, here the volcanic arc, here the deformation front would be to the right here, shows instead a very thick crust of 20-25 kilometers thickness, not 10 like an oceanic crust, all the way through the forearc, showing that first, this is probably the remnant of the oceanic plateau of the Caribbean, which formed over the hotspot, over the Galapagos hotspot. So it's an abnormal crust. And then we have here 60 kilometers of down dip width of this contact of crust on crust. If we go, This is just to summarize these two items. This is the 4-arc crust backstop, the mantle thrust. This is 60 kilometers, can be taken as an approximation to the seismogenic zone, which is much larger than expected from these island arc, say, subduction zones. And the mantle part here is also abnormal. We will see that. So having now the fine approach to the fine structure, fine seismic structure, what about seismic activity? First, the last item is to go deeper, having here the geometry of the upper part of the subduction zone with receiver functions on this little bit wider island of Guadeloupe. We can constrain here the top of the slab here, marked by the negative plus positive swing in the receiver functions as having a kink which goes down here. So where are the earthquakes? In fact, this is a regional seismicity seen by the global network. They are about everywhere, scattered because they are small and so are not well defined, not well located. So the 100 OBS we deployed stayed 6 months, and we have a better approach to this seismicity. And we made a special effort, I will speak about this, where for 4 years we had continuous recording of 9 OBS here, deployed and recovered every few months. And we were lucky enough to be on the site of the largest earthquakes in the last half century, which is a magnitude 7.4 intermediate depth earthquake here, which also activated the whole subduction zone here. Namely, we found for the first time here locations of earthquake magnitude 4 to 5 in the lower plane of what we can call now a double Benioff zone, which is of interest for thermal modeling and so on. This is, of course, thanks to this OBS array, because recording on land is very limited. And we have two other very interesting things, which is one, we have evidence of supraslab earthquakes in the mantle of the upper plate, which is a very rare situation. And earthquakes here, for instance, this is one of the CMT flat thrust earthquakes, the only one which is known, 2008, magnitude 5.3, but it's not located here. With our OBS array, we locate it here, which is on the interface, which brings to the idea that maybe not only the proxy, the usual proxy down to the mantle wedge may be seismogenic, but it might be going deeper. Summarizing here, with respect to the study of Ushida and others before the Tohoku earthquake of the Tohoku region, we see here supraslab earthquakes in the two regions. This is the Lesser Antilles. Here you can, of course, record on land. Here you have to go to sea. We have the flat thrust earthquakes here, deep flat thrust earthquakes under the mantle wedge. And as you may know, these were taken somehow as small asperities which were in a stable sliding zone, but indeed the Tohoku earthquake slip was all along this interplate down under the mantle wedge. So in fact, the similarity of this is up to now not further than that, but the problem is whether this may give the same situation. I think I'm almost out. On the Hellenic subduction zone, this is the tomographic slab, which you see down to the 1,000 kilometers, but in the upper part here you have no resolution. Same for the earthquakes. The earthquakes are scattered by over 50 kilometers and do not define really the downgoing slab. We deployed here, we occupied over 130 sites on land to try to see the slab with receiver functions. And so this is the example. With this 2D array, you can make sections in different directions. And here on this one, which is neither a dip nor a strike line, going from Crete to northern Greece, you see here the top of the slab of the present subduction going down, the upper plate moho here with complications under the Gulf of Corinth due to extension, And here you see probably a top of an earlier subduction, which you can also see on dip lines. These are the dip lines, the blue ones here. You see here the upper plate moho and the present subduction slab. And here, in what would be the mantle wedge, you have also heterogeneous material with crustal material. And so the situation is much more complex than having just a mantle material which can be hydrated or not. By the way, here, this earthquake here, Metony earthquake in 2008, the largest also in 50 years, magnitude 7 about, is a subduction earthquake like the ones I showed for the turn of the last centuries. And so we are in here also, seeing the structure. I think I'm at the end, so I'm going farther. This is an OBS survey we made now to try to have a better approach to the seismicity. The data are not complete, but this is just an example of a pilot study here where with a few OBS we had a gap where the Metony earthquake would occur, and here after with this large deployment where we see the aftershocks. I think I have to stop here. There are a poster session this afternoon on teleseismic converted waves, mostly in the Hellenic, and on Thursday morning, a poster on the Lesser Antilles subduction zones. Thank you for your patience.
Do we have time for a very quick question for the speaker? Do you have any constraints on velocities in the mantle wedge, in the Lesser Antilles?
In the
Antilles, in the Caribbean?
In the Antilles, we have constraints on the upper part from refracted waves, but not at deeper depths, and the receiver functions are too few because these islands are very noisy, so we don't have many earthquakes to model the velocities. We can just say, yeah, thank you.
Thank you. The next speaker will be introduced by our co-convener, Hiroshi Sato.
Okay. Next talk will give by Takaya Iwasaki and others, entitled Structural Characteristics of the Philippine Sea Plates Subducted Beneath the Southwestern Japan Arc.
Thank you, Chairman. This is Southwest Japan. The Southwest Japan is a well-known seismogenic zone where the magnitude 8 class earthquake repeatedly occur due to the northwestward subduction of the Philippine Sea Plate. And in this part here, and a rather young oceanic lithosphere, geologically, the back arc side of the Eastbourne arc is it's died, I guess. Back arc side is, sorry. Thank you.
Press the button, just keep the button pressed.
Yeah. Okay. The back arc side of Eastbourne arc is subducted, and this part is Nankai earthquake source region, and this part is Tonankai earthquake area. And in this area, just east of the Tonankai area, the Tokai earthquake is expected to occur. The Eastbourne arc itself has been collided against the main island since the Miocene time to form a very complicated east collision zone. In the eastern part here, the fore-arc side is subducted, and 1923 Kanto earthquake took place in this part. Another important feature of this subduction zone are non-volcanic tremors and low-frequency events, both of which are strongly controlled by fluids dehydrated from the subducted plate. And these activities are almost terminated around here, west of the east collision zone. And for the last 10 years, intensive active and passive source experiments have been undertaken in this area, from which I like to show you several important structural features. The most striking and common feature in observed record west of the Lisbonian arc is very strong reflection from the Philippine Sea plate. This is the case of the Nankai area, and this part is Tonankai area, and this part is Tokai area. And as red arrow shows, very strong reflection from the top and more of the subducted plates are recognized around here. The amplitudes are very, very higher as compared with the mid-crustal reflections or sometimes the first arrivals. On the other hand, in the eastern part of the, on the other hand, in the region east of the Lisbonian arc, we have such kind of reflection is not so significant. This is the example of the both peninsula. Although we see some reflections from the plate here, but their intensity is very low as compared with the previous cases. So this is the first example of the structural section for eastern Shikoku area crossing Nankai earthquake area. This part here is transverse side, and this part is arcward side, and the Philippine Sea plate is subducted in this way. And the first structural feature is this bulge structure, which is interpreted to be subducted seamount. And from the analysis of the rupture process of this earthquake, this part behaved as a barrier. And beneath of the seamount, the velocity is very small, indicating hydrated upper mantle. The landward of this seamount here, the upper mantle velocity is recovered to be a normal one, and we see a very high seismic activity. Both of these features probably represent the dehydration embrittlement. So the released water are coming up and spread out to form a very thin, several hundred meters and a low velocity, 3 or 4 kilometers per second layer at the top of the plate. And also the magnetotelluric study tells us that low resistivity zone is existing at the top of the plate, strongly supporting the existence of freeze. So this thin and low velocity layer is responsible factor to produce a very strong reflection. The next example is Tonankai area, and this is a section beneath the onshore profile, and this part is a trend side, and this part is arc side, and the Philippine Sea plate is again going down, and the reflections from the top of the plate here, around here, is more or less explained by simple thin and low velocity layer as indicated before. But the reflections in this part here has a coda with a duration time of 2 or 3 seconds, strongly indicate the very complicated reflective zone. And we think this reflective zone is clearly extended within the wedge mantle area. And this green circle here are low frequency events. And so the dehydrated water are rising up and to spread into the mantle wedge to form a very thick reflective zone with a thickness of 5 to 8 kilometers. This is the entire profile of this region. This part is the offshore part, beneath which we have no significant reflections. And the thin low velocity layer or reflective zone are located between the isotherms of 350 and 450 degrees. The next example is the Tokai area here. And the most important phenomena in this region is long-term slow slip occurring at the beginning of this century, which is shown by a dark pink region. And this part here is structural section of beneath the onshore line, and subducting plate is well traced by the strong reflectors, and the low frequency events are concentrated around the wedge mantle. This is also the structural section from the seismic tomography, in which the oceanic lithosphere are characterized by several bulge structures, probably representing a sequence of the subducted ridge. And beneath the long-term slow slip area here, our passive data source, passive source data strongly indicate high VP-VS ratio within this ridge. And this part is researched in more detail by a very dense passive source array observation by Kato et al. And the lower plate is receiver function results, in which the subducted plate and also the land moha are well imaged, and this is the bulge structures. And the seismic tomography results tells us that enormously high VP-VS ratio within this ridge. And just above this ridge, we have also a high VP-VS ratio, but their velocities are also high. So we are thinking that this part here is acting as a cap rock, impermeable cap rock, which prevents the upward fluid transfer. This mechanism works efficiently to accumulate fluid within this part, and also their overpressurization. And finally, they works to decrease the strength of the plate boundary. This plate boundary. This is we think this is the main reason for long-term slow slip event is concentrated in this area. The next example is arc collision zone in here, and the Isbonian arc is collided against our main island, and in this case the thunder block is the Isbonian, one of the part of the Isbonian arc, which is collided against this side, and whose upper and middle crust is scraped off to form wedge-like structures. On the contrary, the lower crustal part is descending down, so we are thinking that the lamination is occurring around here. Then I'm reaching to the eastern part of the subduction zone, and this is the seismic reflection profile west of the collision zone, just above the Great Kanto earthquake. And in this case here, we have in this place we have a Sagami trough at which the Philippine Sea plate starts to be subducted. And here we well developed spray fault system, and here this part is corresponding to the asperity of this Great Kanto earthquake, along which we have no significant reflectors. And reflectors from the plate appeared here, in the deeper part here, but their intensity is very low as compared with the case west of the collision zone. The final example is from the Boso Peninsula, our easternmost profile, and this is results from wide-angle data analysis, and the Philippine Sea plate is defined by the first arrival and the wide-angle reflections. But and this analysis is still continued, but at the moment we have no positive reasons for introducing this producing positive. I have no positive reasons for introducing velocity anomalies, strong velocity anomalies, as shown in the previous cases. So this is our conclusions. Our understanding is very, very increased on the transient structures and the structural heterogeneities on the plate boundary, particularly mechanical interaction or coupling or difference in the fluid system. it is very important to understand the frictional properties, but still our study is remain a qualitative stage, so we have to proceed to more quantitative research by using modeling or simulation. Thank you very much.
Thank you. Are there any questions or comments? Okay, Masa.
So I'm just wondering whether you had any chance to look at the changes in dips along the plate boundary compared to other properties. Has there been anything particularly interesting you found there? With the dip of the plate, with your does that change with any of the structures you've been seeing?
Oh, I have not looked at in such a in such a viewpoint, but we have some of the change in the dipping in this case, and probably the frictional properties is maybe changed associated with the dipping change.
Okay, thank you very much. Let's move on to the next talk. And next talk is invited talk and given by Naoshi Hirata and others. It's titled A New Tomographic Image on the Philippine Sea Slab beneath Tokyo, Implication to Seismic Hazard in the Tokyo Metropolitan region. Please.
Okay, thank you, Chairman. I'm going to discuss on the seismic structure just beneath the Tokyo metropolitan area. As we have already discussed, Japan is located on the subduction plate boundary of the Pacific plate, and also in the southern part of Japanese island arc, we have a Philippine Sea plate subducting beneath southwestern part of Japan. And the Tokyo is just the junction of the two oceanic plates, and there is a triple junction offshore of Tokyo. That's the reason why we have so many large earthquakes in southern Kanto, that is the greater Tokyo metropolitan area. This is the time series of a large earthquake in Kanto area. As you know, we have a magnitude 8 class earthquake in 1923 that we call Taisho Kanto earthquake. And also we have a Genroku Kanto earthquake in 1703. We don't have any instrumental record, but we have the written record in that ages. And we have a large number of magnitude 7 earthquakes in between two magnitude 8 classes. As we have only 2 magnitude 8 earthquakes well documented in history, but the approximate recurrence interval of magnitude 8 is approximately 200, and the previous one is about 100. So the chance of magnitude 8 earthquake in Kanto area is not very large. However, the magnitude 7 earthquake, we have a very large possibility to have. After 1894, this is the oldest magnitude 7 earthquake which was recorded by instrument. We have already 5 magnitude 7 earthquake in 100 years. This makes a very high possibility of magnitude 7 earthquake. For example, we assume a Poissonian time series analysis, and we have a 70% chance of magnitude 7 earthquake in 30 years. And so the Japanese government estimated the damage, the loss and damage by such magnitude 7 earthquake if we have a magnitude 7 earthquake just beneath Tokyo metropolitan areas. It causes more than 10,000 people loss, and also the economic losses in 100 trillion Japanese yen. It's approximately $1 trillion US. This is the old estimate in previous estimate of Japanese government in 2007. However, we have many kind of earthquake, including the megathrust earthquake on the Philippine Sea plate, and also the megathrust on the Pacific plate, and also the Crustal earthquake and intraslab earthquake. And to understand the hazard, we understand exactly where the plates are located beneath Tokyo metropolitan area. So this is the reason why we deployed approximately 300 stations in downtown metropolitan areas. I mean, this is the downtown area, and it's the Greater Tokyo area. And during the 5 years project, we installed 300 stations. Most of them are installed in backyard of schools. And we have a 20-meter shallow borehole instrument and continuously transmitted all the data to the ERI center. And this is an example of seismograms for the 2011 Tohoku earthquake, and we have very large acceleration and also the very large displacement here. And as we have a good system of very large buffering system and batteries, we can continuously record all the main shock and aftershock of Tohoku earthquake sequences. And what we have done is to do a tomography study. This is the comparison between the tomogram before the installed new seismic stations, and this is after seismic stations, 300 seismic stations. And we can clearly image the Philippine Sea plate is subducting beneath Tokyo metropolitan areas. So we got a 3D, very detailed seismic structure. This is an example of the VS, S-wave velocity structure, and we have an image of the Pacific plate is subducting, and also we have an image of the Philippine Sea plate somewhere here, and I plotted both the microseismicity, and we estimated the configuration of the Philippine Sea plate and Pacific plate. It's approximately 1,000 seismic data to image seismic structures. And we have a collision between Philippine Sea plate and the Pacific plate at a depth of approximately 50 kilometers, something like this. And this contributes megathrust type earthquake and also intraslab and crustal seismicity. Okay. So the first implication of this kind of study is to image the plate geometry beneath the Tokyo metropolitan area. This is a cross-section along the Tokyo Bay to downtown Tokyo. It's the northern tip of Tokyo Bay. And this is the comparison between the previously estimated Philippine Sea geometry, and this is the new geometry of Philippine Sea plate. So what we found is the real depths at the northern end of the Tokyo Bay. The Philippine Sea plate is approximately 10 kilometers shallower than previously thought. This is seriously for the people living here because the source is closer to the surface. And then this is the comparison between the old estimate of the intensity distribution by the Cabinet Office and this is the estimate done by the new data set. So this is the JMA intensity scale. The 7 is the maximum of the scale, and we have small areas of intensity 7, and also the area of intensity 6 plus extended westward here. Okay, the second implication is we got a preliminary new pathological model which suggests a thermal and rheological constraint. It is important to do a geodynamic modeling, for example, to understand the effect of the 2011 Tohoku earthquake to the metropolitan areas. What we have done is to using the tomography image for the P wave and the S wave and VP over VS, and we estimated the log types. And for example, this is the west-east cross-section, and we can image Pacific slab is subducting beneath Tokyo metropolitan areas. And we have downgoing oceanic crust, and there is a change from the velocity to the ecologized system. And if we use a phase diagram for the rock types, and this is the phase diagram for the mid-oceanic ridge basalt, and from these diagram we can estimate approximate temperature at the phase boundaries from here. So, and we have a reaction, dehydration reaction at the Pacific slab, and we can estimate fluid migration from dehydrated fluid into the mantle wedge of Philippine Sea plate. And this will generate a serpentinized peridotite system, and also those fluid will affect the materials in the Philippine Sea plate here. And this is a north-south cross-section, and the Philippine Sea plate is subducting. Also, the dehydration reaction occur at about this depth, and the rock type and the temperature is different from the Pacific plate and the Philippine Sea plate. We can estimate it approximately 600 degrees C temperature at the closest to the ecologized system here. Because the Philippine Sea plate is younger than the Pacific plate, and the temperature is higher than the Pacific. This is consistent. And of course, exactly speaking, the Philippine Sea slab here is not oceanic crust, but Isabonina arc is an island arc system, so we cannot use this diagram directly. So we are now working on the laboratory experiment to measure the velocity of the rock from this type. Okay, and also this is the distribution of VP over VS. This is the VP structure, and this is just above the Philippine Sea plate, which controls the rheology of the plate boundary of Philippine Sea plate. And what we found is some area has a large degree of serpentinization in this area, and also the VP-VS ratio is very high, and we can estimate some distribution of fluid in that areas. So this can be a barrier for the megathrust type earthquake which may occur in the Philippine Sea plate, like 1923 Kanto earthquake type earthquake. And however, the serpentinized area is limited at the very northern tip of the Tokyo Bay area. So we do we may have down dip limit is slightly lower than what we estimated before. Okay. In summary, we have many large earthquakes in Kanto area, which simply because we have two subducting oceanic plates. And the Japanese cabinet estimate a large losses in Tokyo metropolitan area due to the hypothetical event beneath Tokyo Bay, northern Tokyo Bay. We developed the Metropolitan Seismic Observation Network, so we call Mesonet. Approximately 300 seismic stations are installed so far, and which reveals the structure of the Philippine Sea Plate and the Pacific Plate, and estimated about 10 kilometers shallower than before we thought. And if such an northern Tokyo Bay earthquake occur, and stronger ground motion will be than previous thought. And also we have such as the estimate has been used to evaluate the seismic hazard in area, and we have a new petrological model proposed, and which may be used to constrain the thermal and rheological structure. Thank you for attention.
Okay, please.
Yes, you showed you have earthquake between 1700 and 1923. Many quakes, you told them magnitude 7 plus. Do you have any historical information about damage these magnitude 7 affected Tokyo area? Of course, not the highly populated probably, but any information about that. Also, your estimate of 11,000 dead looks like very, very conservative, considering you have mapped that the boundary now 10 kilometers shallow. Are you sure that's only 11,000, or are you trying to please your government?
Okay. We have magnitude 8 earthquake in Taisho and Genroku. It's a 1703 earthquake. We have a written record of the damage in the old Tokyo. We call Edo area. So, and also we have several magnitude 7 earthquake, including 1855 or something. It's Ansei Edo earthquake. It's magnitude 7. It's more than 700 people was killed by this earthquake, and lots of damage due to magnitude 7 earthquake. We do not have a written document for previous magnitude 8 earthquake, but we have a geomorphological or geological evidence for magnitude 8 earthquake in Kanto area. So.
Okay, let's move to the next talk. And next chair will switch to the Martha Savage.
Thank you. Our next speaker is another one heralding from New Zealand. That's why I'm introducing these new people. This is given by Carolyn Holden. It's about It's Our Fault, Better Defining Earthquake Risk in Wellington, New Zealand. And its first author is Russ Van Dissen. Thanks.
Okay, and that's the pointer. Well, good morning. So I'm presenting today an overview of the It's Our Fault research program, and I'll be focusing particularly on the results from ground motion modeling for subduction interface earthquakes. Okay, so the It's Our Fault program is aims at positioning Wellington to become more resilient against earthquake hazard, and in doing so through a comprehensive study of the likelihood of large earthquakes around Wellington, the effect of these earthquakes and the impact on the humans and the built environment. So now the program's been running for over 6 years now, And I've just listed some of the key results that include better understanding of the location, the size, the timing and the likelihood of large earthquakes around Wellington, the stress interaction between those faults, modeling of the subduction interface that I'll be presenting later on, geological, geotechnical, and geophysical characterization of the basin, Wellington Basin, and near-surface sediment, and finally, ground shaking characteristics with regard to the subsoil classes relevant to the New Zealand building standard. So these are some of the key results from the ITSAF program. And today I'll be focusing on subduction modeling. So the talk will start with the Wellington earthquake setting, presentation of the earthquake setting. Then I'll present the proposed rupture scenario, and finally we'll look at the synthetic seismograms and synthetic response spectra. Okay, so the Wellington region is cut by a number of large right lateral strike slip faults, and it's also underlain at about 23 kilometer depth by a subduction interface currently locked and west tipping and separating the Pacific plate and highlighted by the overriding Australian plate. In the recent historical time, which is for New Zealand about 160 years, the region has experienced one large crustal earthquake. However, we've never experienced any subduction earthquake near Wellington City. However, the subduction interface is potentially the largest earthquake hazard in New Zealand, but we have a lack of historical recordings, we have a lack of geological data, we have a lack of real-world ground motion data for this very specific tectonic context. So how can we characterize the hazard from that interface as well as the risk? So a proposed solution is to do synthetic ground motion modeling using a proposed rupture scenario. And for this, I've used the stochastic modeling code XSIM. But again comes the question of how do you characterize potential rupture scenario on an interface that is mostly blind? So what kind of earthquake source are we going to use for the model? And in terms of the location, the size, and the magnitude. Well, a good place to start is to use the map from the Wallace et al. Study in 2012 that highlights the contour of the locked interface for the Hiurangi subduction area. So in red color is the intensity of the slip rate deficit for the interface, or you can call that the locked region on the interface. So we're going to start with that map to try to identify some potential rupture scenario. So the first proposed scenario is a simple fault plane as derived from the study of Sterling et al. 2012, with the scenario that has most likely the most impact on Wellington City. And it's a magnitude 8.4 earthquake rupturing a 220 by 144 square kilometer area, equivalent to magnitude 8.4. The geometry is fixed, but you can actually vary some rupture characteristics. Still, you can vary the stress drop. So from the study of Atkinson et al., you get a whole range of potential stress drop on subduction regions. But you can also, interestingly, Wellington is actually located on the southernmost side of the potential rupture interface. So by changing the starting point of the rupture, you can imagine you're going to influence on the ground shaking in Wellington. So you can also vary the hypocenter location. And so I've entertained 4 different scenarios, extreme scenarios, where you can, to see the impact of the starting point on ground shaking in Wellington. Now, if you look carefully, you can see that there's actually a region right near Wellington City that is actually of higher intensity in red color. So there's actually potentially an asperity located right beneath the Wellington region. So this is why we've entertained a second type of rupture scenario where we assume an asperity-like rupture. And based on the study of Irikura and Miyake 2011, we assume that most of the ground motion will actually be generated by a smaller but area with higher slip amplitude and higher stress drop. So the intensity asperity in this model is equivalent to a magnitude 8.2 earthquake with a rupture size of 90 by 90 square kilometer. And finally, we've been using historical past events. We just assume we ignore whatever's going on the Hiurangi plate, and we're going to use detailed slip history from past large earthquakes in subduction regions. So what we've done is we've taken detailed slip history from the Tohoku earthquake in 2003, and we basically just take that slip history and we paste it onto the Hiurangi interface, respecting the conditions that you can't have any slip passing the subduction boundary zone, and we're trying to keep the asperity located next to the potential asperity near Wellington City. In this model, the maximum slip is about 4 meters, and the rupture starts up deep and propagates down deep. We've done the same for the Sumatra earthquake. We've taken the slip distribution from Chenji 2005, which is equivalent to magnitude 8.9 earthquake. And we've taken the slip history, pasted on the Hiurangi interface. And in this model, the maximum slip is nearly 20 meters. And the rupture starts to the north and ruptures along strike to the south. And finally, we've taken the slip history from the 2012 Chile earthquake. In this model, the slip history is characterized by a maximum slip patch of about 9 meters next to Wellington City, and the rupture starts in the middle of the fault plane and propagates bilaterally. So using all this proposed scenario that I've been through, we've computed synthetic accelerations and synthetic response spectra that are shown in this slide. So on the left-hand side, you've got the model seismograms for the various scenarios I've been through. And on the right-hand side, I'm going to show in a minute the response spectra for these various corresponding scenarios. The response spectra represents spectral acceleration on the y-axis and periods from 0 to 10 seconds on the x-axis. And they will be plotted against spectral shape for design level on firm site condition in Wellington City. So the bottom curve represents the spectral shape for normal type, for the design of normal type buildings, whereas the top shape represents the spectral shape for critical structures, which are structures with post-disaster functionality or dangerous activities. Okay, so we just go one scenario by one. So first we'll have a look, as you remember, the simple fault plane, but I just vary the stress drop. And so we've entertained a whole range of stress drop values. I'm only showing the two extreme lowest stress drop and a higher value of stress drop. You can see that uncertainty in the stress drop leads to a factor of 3 in terms of peak ground acceleration in Wellington. If you look at the response spectra for the lowest stress drop scenario highlights deficiencies for the design level of normal structures from 2 seconds and beyond. The higher stress drop scenario highlights deficiencies at all periods for normal structures, but especially deficiencies for critical structures for 0.5 seconds and beyond. Now we look at the influence of the starting point on ground shaking in Wellington. So first we look at the model seismograms. The top two purple curves represent a rupture starting to the north and rupturing to the south, and the bottom two curves represent a rupture starting to the south and rupturing away from Wellington to the north. You can see some obvious directivity effects. So the top two seismograms have shorter duration but larger peak ground accelerations, whereas the bottom two seismograms, so rupture going away from Wellington, have longer shaking duration and smaller peak ground acceleration. However, if you look at the response spectra, they're all very similar, and they highlight deficiencies for critical structures for 1 second and beyond. We now look at the asperity model. So for the asperity model, again, large peak ground acceleration of almost 0.5 g, and again, deficiencies for critical structures for about 0.8 seconds and beyond. Finally, we look at historical earthquakes. So if we look at the seismograms for the Sumatra, Chile, and Tokashi in that order, interestingly, the largest peak ground acceleration are generated by the Tokashi type scenario, about 0.7 g, which is the maximum PGA computed from all the scenario. And it's likely due not to the slip distribution, obviously, but from the stress drop that was used in the model. This is the largest stress drop of all the historical scenario. And as expected, the Sumatra and the Chile earthquake have the longest rupture duration, shaking duration in Wellington. If we look at response spectra, so for the Sumatra, Chile, and Tokashi earthquake, again, all of these events highlight deficiencies for normal structures at all period and deficiencies for critical structures at period of about 1 second and beyond. Okay, So to sum up the talk, those proposed rupture scenarios were pretty simple. However, they highlighted that you can expect a long duration ground shaking as well as large peak ground acceleration in Wellington. They highlight as well the deficiencies in the current design level in Wellington, especially for extreme events. They've also highlighted that stress drop is a critical factor, so uncertainty in stress drop led to a variation of PGAs of about a factor of 3. And if you'd like more detail, I invite you to the poster on Wednesday afternoon. Going back to the Itself project, obviously we can see that the project has had a great impact on building up resilience for Wellington against earthquake. And especially for subduction earthquake, where it was the first one to instigate research study on ground motion modeling from subduction interface. We obviously need to better define our source model for the subduction. We need to better define the ground motion modeling. And this will be done through the past findings from the Itself research program by including site effects and basin modeling that were findings from that program, and also using results from future research theme of the project, which are including the topographic effect and also developing ground motion prediction equation for engineering application. Thank you.
Thanks, Caroline. Are there any questions? We have time for a couple. Yes.
Have you compared the design response spectrum from countries that have subduction zone earthquakes, like Japan, Chile, against your Wellington design response spectrum?
No, I haven't. I think so the subduction hazard is a newly recognized hazard, and also the context of in terms of convergence rate and the location of the large city right above a subduction interface is a very particular settings. So no, I haven't, and I don't know if it would be relevant.
One more question. I'm wondering if you have, so all of your design spectra seem to be failing for the large periods. And do you have an idea of what is actually happening there, why, and whether there's going to be any fixes in the design codes?
Yeah, I guess that's what we're hoping to do. This is a study at its early stage. This is actually more like an eye-opening on what's the design level compared to this newly recognized hazard that is the subduction hazard. So yeah, definitely there'll be development, collaboration with earthquake engineers to try to develop a new set of design levels for Wellington. Yeah.
Right. Thank you. We'll have to move on now. Our last speaker is also from the same organization. Stuart Henrys will talk about the 2009 to 11 Sake experiment, 2D velocity imaging across the interseismically locked southern Hiurangi margin, Wellington, New Zealand. It's an invited talk.
All right. Thank you very much, Martha. And you can see from Carolyn's talk that New Zealand is very interested in the subduction thrust and its response, particularly in the Wellington region. So I'd like to acknowledge some of the contributors to this study. There's been a large number of organisations that have contributed. So the Sake experiment, the seismic array Hiurangi experiment, we wanted to really challenge ourselves to try and understand what the physical properties on the plate interface are beneath Wellington. We wanted to understand the role of upper crustal faults and their role in controlling tectonics across the lower North Island. We wanted to really get to grips with mechanical conditions adjacent and on the plate interface, and we wanted to compare and contrast the locked part of the subduction zone to the area to the north along the margin, and finally, what are their lessons that we can learn from this subduction zone to others. So I'll cut to the chase. We've still got work in progress. There's a lot still to do. Can we say something about the roller upper crustal faults? Yes, I think we can. Can we say anything about the conditions on the plate interface? Well, perhaps yes, perhaps no. And we can make some comparisons along the margin, and then we can perhaps share some thoughts about other subduction zones as well. So you've already seen the underlying map. So I've superimposed the slip deficit, the plate coupling, you can see on the plate interface. So this is work from Laura Wallace. See, this blue region here is unlocked, and the region here is locked beneath Wellington. So what I've done here is showed all the seismic sections that we've accumulated along the margin. Just a bit of tectonics. We have the Pacific Plate. It's the Hiurangi Plateau. It's a thickened oceanic crust dipping beneath the North Island of New Zealand, the Australian Plate. So from all of those seismic work we've done, we hope we can say something about slip on the unlocked part of the margin, this transition zone, and across Wellington. So I'm going to be talking mainly about this experiment here, Saki, and principally about this transect through here. So what we did this in two phases. We had a multi-institutional support for this. We had a multi-channel survey that Crown Minerals collected. It was about 4,000 kilometres of multi-channel data, and we put OBSs out along the central part of the transect, and we did that in 2009 and 2010. We also had, for about 6 months, we had an array of instruments from IRIS that were out over this lower part of the North Island. And then, so for this transect part was an onshore-offshore experiment, and then we came back in 2011 and had 12 shots through here, and we instrumented about 1,000 stations across the central part of the transect. We also located ourselves on some previous broadband array, and I'll refer later on to the station W3. We also capitalised all of the shots from both experiments into the permanent GeoNet array here. For each of the shots, we had about 50-metre boreholes and about 300 to 500 kilograms of explosives. So I'm going to put, just to key into the profile here, we had a large event, magnitude 8.2 in 1855 in the Wairarapa. So this Wairarapa event was pretty much in the central part of the profile, and I'll refer to that event partly in this talk. So this event in 1855, it was a large event. It uplifted approximately 3 metres along this part of the fault, ruptured about 140 kilometres of the fault, and uplifted a huge area which tilted back to the west. So you can see these uplifted terraces at Tarakirai, and they had a strike slip displacement of 80 metres at this point. So there's been various studies on this fault, and I refer to this Derby and Beanland. They a best fit dislocation model to the uplift that was observed is this kind of Listric fault that pretty much merged down into the plate interface at about 30 kilometres depth. Also, GPS observations from Derby and Beanland, and also Laura and Wallace, it shows that this part of the plate is locked, and that Wairarapa fault pretty much verges in a Listric nature down to about the edge of that locked region, again about 30 kilometres depth. So that was a cross-section east to west. So this is a stack of those 12 shots that we recorded in the second part of the experiment. So this was to the west, this is to the east, and you can see a number of features in that from the 12 shots. You can see this thick band of reflectivity, but the top of this reflectivity zone shows quite a sharp reflector, which I think merges in a Listric nature up, and we can interpret that as the Wairarapa fault. We can also see a number of other striking features within that package, and some of them appear to be other splay faults that we can map to the surface, and they are to the west of the east of the Wairarapa fault. We can see the plate interface. It's not very distinctive out to the west, out to the east, sorry, but becomes strongly reflective beneath the Tararua Ranges, and we get a hint of the base of that Hiurangi plateau. That's the base of the oceanic crust that's subducting. So I've put an interpretation on that, and it's superimposed on that as our first arrival travel time tomography, which I'll come to in a minute. And I've just highlighted that region just to show you the high reflectivity that we have in this region. So for the first arrival tomography, we picked nearly 18,000 pics from the first arrivals from both the onshore and offshore gather. This just shows you one super gather for the shot, the onshore receiver, and the shot at that location. So we had very good first arrivals. We had perhaps PN arrivals out onto the west coast, but we've used all of those arrivals to construct a first arrival tomography. We've done checkerboard tests which show that this structure is fairly well constrained for about 20 to 25 kilometres. It's not that well constrained at depths more than 30 kilometres depth. We can see a number of features already observed in this. We can see that the Hiurangi accretionary prism is quite low velocity. Out onto the Taranaki platform, we see faster velocities, and we can see the subducting Pacific plate going down. I also put here the MCS profile on the eastern coast and on the west coast, and obviously in this time of talk I can't put a lot of detail into all the arrivals, so I just kind of refer occasionally to, we have a poster in this morning's session, and I just wanted to really highlight in this talk the plate interface reflector and some of the other major reflectors. So we can see from the NCS profile in particular, so we can see a large accretionary prism, but we can know that the faults on that prism detach at this interface, and we can see beneath that interface about 3 to 4 kilometres of sedimentary channel. So I just wanted to highlight how we have constructed our interpretation. I've just taken one of these crustal events observed on 3 different gathers, and we've migrated that event using the first arrival tomography. So these are migration ellipses, if you like, and I've taken the envelope of those ellipses to construct the major reflectors. And that's the reflection interpretation of that crustal, the P-crustal event that I've interpreted here. So the envelope of that P-crustal event, you can see the Wairarapa fault has that listric nature. So there's a number of features that I've taken here. I've taken all the interpretation. The top of the plate interface, that PIP interface, is not very distinct, but we can track it from the MCS going down a distance of about 100 to 160 kilometres, and then it makes quite a sharp bend in this area that we have low velocity. We have the Wairarapa structure that I've referred to before. It seems to be dipping nearly 40 degrees at the surface and appears to be listric. We can see the top of the moho on the Pacific plate is quite distinctive in our first arrival tomography. And we get a hint on both the multi-channel data and the tomography that perhaps we can see the base of the plate interface. What we've also done is, Kurashima-san has a poster on this later this morning, is that we've taken not just the pics, which I've used in the tomography, but we've taken all the reflection data from the 12 shots, and we've done a migration, a scattering migration of that. So I've put his scattering migration result up here, and I've put on the interpretation that I made from the pics and from the MCS data. And so you can see there's a very good correlation that we can confidently say a little bit about the plate interface. We can clearly see those splay faults in the upper part of the crust, and we think we can now resolve the Wairarapa fault down to the plate interface. So I want to say a little bit more about the low velocity that we observed. So this is this broadband station on the Tararua Array that Martha recorded and reported on in 2007. So in that In that box here, I show the data for W3. I show her model, the tar model, that is at that place, at that line here, at W3, and I also show the velocity model that we recorded by just extracting a section through our first arrival tomography. So this is a result of a model for her tar array that tries to fit not just the W3 data, but all of the data. And these are two models that I've constructed for the same array, just using the first arrival tomography. So you can see that the receiver function data records a very good P-way arrival and a reflector here at about 5 seconds. And intervening, there's this low velocity, low reflector, this reverse reflector in here. So Martha interpreted that as a layer that is about 24 to 28 kilometers thick and has quite low velocity, and that was the model she got. But I think we actually get a slightly better model fitting that same data with our low velocity here in the upper crust. And we can tune down VPVS and get even a slightly better amplitude map matched to the observed data. But this is not very well constrained. So I put some of this information together in a series of kind of main points. We have the subducting sedimentary channel, which I think is underplating. And the model we have for that is that I think that the sedimentary channel that is defined from the MCS is then cut through in a region that's under this high reflectivity, and it is allowing this package of stacked reflectors that we see on the MCS to be this underplated region. So I think that those sediments, that high reflectivity sediments, reflect this underplating and ramping, allow you to ramp up the Wairarapa fault underneath here. We also think that that those trapped sediments perhaps are forming a cap, allowing VP-VS ratio to be high in this part of the subducting slab. So you get perhaps dehydration embrittlement, allowing fluids to be trapped. And here this is work of Don Eberhardt and Phillips and Martin. And I think that the seal for that trapping is these sediments. These sediments also appear to have this region of low Q. Q is about 400 in this region. So I think that low Q from Q-wave tomography is reflecting these underplated sediments. Wairarapa fault, it's steeply dipping, listric event, and appears to bound the upper surface of that high reflectivity, and appears to be listric and merge with the Australian plate at about 32 kilometres down dip of the strongly locked region of the plate interface. So the big question is relationship to locking. So I could suggest that there's an increase in dip. This is not that well constrained, but perhaps it defines the locked part of the plate region where the plate is dipping shallowly. This is about 5 to 8 degrees. This reflects the locked part of the interface, and where there's a change in dip, this may be a transition from the locked to unlocked part. And then I kind of throw this out there in that a comparison of New Zealand, North Island New Zealand and southwest Japan. There's a suggestion that perhaps where the plate is dipping shallowly and then steeper, this may mark the transition from locked to unlocked, and that we know that the plate is more steeply dipping to the north, and maybe this locking pattern is a first order constraint on the plate. It basically seen the plate dip changes. And I make the provocative suggestion that perhaps the plate interface locking in southwest Japan also reflects that change in dip. So in conclusion, we have developed a two-wave P-wave tomography model across the lower part of the North Island, about 350 kilometres in length. We've imaged stacked sheets of the sedimentary material at the top of the Hiurangi Plateau, and we think that's subducting into the footwall of the Wairarapa fault, and that we can suggest that an increase in the angles of dip perhaps reflect those stable to unstable transitions. And I'll leave it at that. Thank you very much.
Thank you, Stuart. We're running a little bit late, but we'll have one quick question, if there is any. Yes. Well, thank you for that comment. I hope perhaps you could be on our committee next time and really get the South American people to come. We had trouble getting them to come. But anyway, come and see our posters this afternoon. And actually, there's another session in about 20 minutes in the same room, which is on a very similar topic. And that session title is, How, when, and where does slip occur in the subduction environment? So it's a very similar topic, and yeah, hope to see you. Thanks.